Welcome to Maths TV! Maths TV, it's fun for us, it's fun for you, it's fun for me. Maths TV, it's fun for the family.
Math. The word mathematics originally comes from this Greek expression, ta mathemata. Ta mathemata means things we gain by taking, but it's not the taking in the ordinary sense. It's the taking of what we already have. So we usually take something that we don't have, but ta mathemata means things we gain by taking, but the taking is the taking of what we already have. Well, this is difficult. In other words, mathematics in its original sense means the taking of what you already have and the knowing of what you already know. So what does that mean? There's a Japanese mathematician called Oka Kiyoshi, and I hope everyone will remember this name after this presentation. He used to be in Kyoto, and he's one of the world's most known Japanese mathematician. And Oka was actually so great that some people in Europe thought that Oka was the name of a group. They couldn't believe that he did all this job by himself. Just one single person did all this job. They couldn't believe it. And Oka was not just a great mathematician, but he was also a profound thinker and philosopher. He has left some great quotes and beautiful essays on the nature of mathematics. And in particular, he repeatedly said that mathematics can say nothing of the first number 1. Well, obviously, numbers are the most simplest objects in mathematics. But if you try to explain why the first number 1 has to exist, or what the first number 1 is in the first place, no matter how hard you try, mathematically or logically, you will never be able to explain or never be able to prove the existence of the number 1 or what the first number 1 is. We simply believe it. It's the believing of something with no grounds.
Algebraic!
Of what's true in mathematics is not governed by rules. And whatever rules you lay down, you can always transcend those rules. If you accept the rules, you can see how to go beyond them. And this is amazing. It's really hard to see that you could say, okay, maybe all we do is believe these axioms and these rules, and that's all we do. And then Gödel says, no, you have to believe this too. If you believe those rules, you must believe this other thing, which is beyond the rules. So what's going on, you see? If it was, and this rules, Turing, in his idea of a computing machine, showed, idealized what rules mean and what it is to follow a computation. And this is a way, somehow it shows that the mind, in our understanding, whatever understanding means, is not something you can encapsulate in a computation. So this idea had been with me for many years.
These are ideas that are talked about a lot at the moment in cognitive neuroscience and systems neuroscience. There's a kind of perfect place. There's a perfect balance between kind of formlessness or complete disorder and complete stability, but stability to the extent, or order to the extent, that the system then becomes inflexible. So for consciousness to be poised in this kind of optimal place, where we can scrutinize the world in the best way, learn the nature of the world in the most optimal way, and yet retain flexibility given that the world is changeable, then there's a kind of sweet spot where the system has to be, where it's perfectly balanced between disorder and order.
He uses these examples in his book of all these famous mathematicians and physicists that, like, when they wanted to solve some problem, the key is they think about, okay, I'm going to solve that problem, and then next step, stop thinking about it and let it percolate. Get the mind out of the way, let the subconscious, metaphorical, perhaps it's limbic, let that system work on it, and then spontaneously it will start, and that's what they talk about with this entropic brain function. You get into these other stages of possibilities where like avalanches of networks start happening. You know, things start coming together in ways that your mind can't keep up with, but that we're actually designed to do those things.
Mathematical!
The statement here is that the perception of mathematical truth cannot be reduced to a set of mechanical rules. And this comes from a famous theorem due to Gödel, and Turing was certainly very familiar with this. It featured very much in his 1936 paper, the original one, because he was very much concerned with things that computers couldn't do, if you like. That was part of what he was trying to do. And so as to say what you couldn't do by a mechanical procedure, he had to define what he meant by a mechanical procedure and then show that there were certain things that you can't do with a mechanical procedure. Well, I'm going to phrase Gödel's theorem in a way which it's not normally phrased, but it is a perfectly correct deduction from his theorem. Tells us that for any mathematical theorem, and that's the kind of thing I'm talking about here with natural numbers and so on, it tells us for any set of mechanical theorem-proving rules, and when I say mechanical theorem-proving rules, I mean you have a set of procedures which can be checked by a computer. That's the crucial point. If you follow these rules and you come to a conclusion that it proves some mathematical statement of the kind we're talking about, then that alleged proof can be checked by a computer. So that's the kind of rules we're talking about. Then what you can construct is a particular mathematical statement, which Gödel shows you how to do, and I'm calling that G of R, which if we trust the rules, if we believe in the validity of the rules, that is to say, if we believe that anything we derive using the rules must be true, if you trust the rules, then you must also believe that this particular statement, G of R, is true. Yet, it cannot be proved using the rules. Now, that's a very striking, remarkable thing, because what it's telling us is that whatever these rules are, if they're rules whose consequences we believe in, then that belief or that trust extends beyond the rules themselves. And you have to know that the rules are trustworthy, and that belief that they're trustworthy enables you to extend beyond the rules, so that this particular statement, G of R, cannot be proved using the rules of R, but the way in which it's constructed tells you that it's nevertheless believe it's true. See, people usually state Gödel's theorem in a rather negative way. They say there are certain things you can't prove. But what they mean is you can't prove using a very specific set of rules. But if you trust those rules, then you can see that statement is true. And this is a very striking thing about the Gödel statement. And clearly Turing was very much aware of this, and that
Now, what I'm going to quote to you is not from any of Lusen's published works, but the marginalia that he made as he was studying certain mathematical problems. It was written about 1915, and this is about the same time, 1415, that he established, together with Dmitry Yegorov, the seminar that became the cradle of the Moscow School of Mathematics, probably the most famous seminar in the history of mathematics, usually called Lusitania. There's another story behind that. Anyway, so Lusen wrote this in the margins as he was studying a mathematical problem in set theory. Quote, "Each definition is a piece of secret ripped from nature by the human spirit. I insist on this. Any complicated thing being illumined by definitions, being laid out in them, being broken up in pieces, will be separated into pieces completely transparent even to a child, excluding foggy and dark parts that our intuition whispers to us. By separating the object into logical pieces, then only can we move further towards new successes due to definitions," unquote. By linking naming to mathematical definition, and by describing definition as, quote, a piece of secret ripped from nature, unquote, Luzin revealed his differences both with traditional mystical views of naming that I've already discussed a bit, and also with Western rationalism, especially the French form so followed by his mathematical colleagues in Paris.
Mathematical!
Without this power of our mind of believing things, math will be totally groundless and meaningless. So at first sight, math seems to be about numbers and calculation and logic and all that stuff. But underlying calculation and logic, there's this huge dimension in our minds that underlies all calculation and logic. So at the heart of mathematics, there's not numbers, there's not logic, there's not calculation, but there's this huge dimension, our inner universe, which Oka Kiyoshi called Jocho. And Jocho is a difficult Japanese word. I was looking for a good translation for it, a good English word that corresponds to Jocho, but unfortunately I wasn't able to find one. So let's just call this Jocho. Jocho. So in Oka's terms, math is not about numbers, math is not about calculation, math is not about logic, math is about Jocho. It's the very act of looking inside your mind and, well, encountering with your own self, encountering with your own rich inner universe, your Jocho. So if you want to do mathematics, pick up a problem. It doesn't have to be a difficult one. You don't even have to prove a theorem that no one has proved yet. Just pick up a problem, it can be an easy one, and concentrate on it. Try to solve it yourself. Don't look at the answers, don't cheat. Keep on thinking about a problem until you figure your way out by yourself. Then, so you have to be patient, you have to keep on paying attention. Being patient and keeping attention on one subject is very important. And during this mindfulness, you'll find yourself encountering with your own mind. And if you're lucky enough, you'll find yourself swimming around in the sea of Jocho inside your mind. Well, try it if you have time. So, this was a very short presentation on mathematics. And basically, I only have one message. Math is not about numbers. Math is not just about calculation. Math is not just about logic. Math is the very act of looking inside your mind and encountering with your inner selves, with your inner universe, with your inner rich whole dimension of Jocho. So in this sense, everybody, including you, can be a mathematician. Thank you very much.
What's 2 plus 2?
A billion. When we have a system like Rule 30 or like the system here, like something in nature, we can think of it as doing a computation. In effect, we feed in some input at the beginning, then it grinds around, and eventually out comes some output. Then the question is, how sophisticated is that computation? Well, we might have thought that as we make the underlying rules for a system more complicated, the computations it ends up doing would somehow be progressively more sophisticated. But here's the big claim of the principle of computational equivalence, that that isn't true. Instead, after one passes a pretty low threshold, and one has a system that isn't obviously simple in its behavior, one immediately ends up with a system that's doing a computation that's as sophisticated as anything. So what that means is that all these different systems, whether it's Rule 30 or whether it's a fancy computer or a brain, they're all effectively just doing computations that have the same level of sophistication. Well, okay, so there's an immediate prediction then from the principle of computational equivalence. There's this idea of universal computation. It's really the idea that launched the whole computer revolution due to Alan Turing and friends. You might have thought that any time you want to do a different kind of computation, you need a different system, completely different system. But the point of universal computation is that you can have a single universal machine that can be programmed to do any kind of computation. And that's what makes software possible, and that's the foundation for essentially all computer technology today. But okay, the principle of computational equivalence has many implications, but one of them relates to universal computation. It says that not only is it possible to construct a universal computer, but actually it's easy. In fact, pretty much any system whose behavior isn't obviously simple will manage to do universal computation.
Mathematics, 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 mathematics. Drop out of school, learn mathematics.
drop out of school and learn mathematics.
But does randomness actually save free will? And many people have chatted about this, okay? My claim is that actually this question about determinism and randomness, which goes in philosophy under compatibilism and incompatibilism, really doesn't have much to do with free will. What is free will? Or rather, not free will in general, sorry. This sensation, our inability to predict our own actions and our own decisions. Let me just talk about that. Where does that come from? Well, I mean, as was pointed out by Marcelo, that you know, now we've got these neuroscientists, poke around in our brain, know what we're going to decide like a few minutes or a few seconds before we do it. So they go walk around saying, hey, we don't have free will. Actually, Stephen Hawking says this as well in one of his books. I have a good Hawking quote about this. Completely wrong. Here's a poor brain. I mean, come on, a poor brain, all right? So why is this not true? I claim that the origins of our inability to predict ourselves lie in the halting problem. Here is a Turing machine. The Turing machine is simulating itself, simulating itself, simulating itself all the way down the line, like, and you know, what the heck is that? So, the halting problem, what is the halting problem? If we have a Turing machine and it starts to ask itself questions, it says, will I ever be able to answer the question, or whether I'll be able to answer the question, I wonder what the answer is. And I claim, and I will give some strong evidence, and in fact some mathematical theorems. I will not show you the theorems, but basically this result gives a mathematical theorem that proves that shows that this is the basis for our inability to decide what's going on. So in fact, if you have finite resources, so Turing halting problems comes from having infinite resources. Let's look at finite resources. Here's a rather attractive, I believe, woman contemplating modeling herself, thinking about herself, thinking about what she's going to do. And you see, just to be able to draw this in 2 dimensions, I had to make the things in the thought bubbles less detailed than the woman herself. And that's because if you try to model yourself, your models will be less detailed than you are yourself. And there's a very nice set of theorems from computer science that capture this beautifully.
Algebraic! That's certain. So I can't see how this very sophisticated, very precise, unknown, unknowable algorithm can have come about through natural selection. So I leave you with that challenge. And it seems to me it's a big challenge. So what's been going on then? What was selected for if it was not a complicated, unknowable algorithm for doing things, arithmetical problems, which I can't believe? What it was, I think, is consciousness. You see, I would argue that consciousness, well, you see, it has many manifestations. Passive things, qualia, perception of the color red, or appreciation of a melody, or so forth, or active, free will, all these things. All sorts of words here which have to do with consciousness in one way or another: pain, love, red, pride, determination, intelligence, disgust, etc., etc. I want to concentrate on one word, that's understanding. And also only understanding in a very specific context, namely the one which you use to derive the validity of G of R and the fact that it can't be derived from R. In fact, I'm going to give you this argument later on, so wait for it. That's the hardest part of what I'm going to say, but I'll give you the argument. So it's not something which is that difficult. I mean, I'll give it in outline. And the basic point is understanding of what you're doing. And you can't, it seems to me, formalize understanding in terms of a purely computational system. And here is you, I say, is a computer or computer-controlled robot capable of genuine understanding? Well, this kind of question has come up here. And whether you could test for understanding is one question, and that relates to the Turing test. Say, can you ask your computer or person, whichever it is, a question which requires understanding in the response, and that's the sort of thing that computers tend to lack.
According to the ancient Greeks and many later mystics, naming was a way to gain a power over a thing that you name. But Luzin believed that naming was a two-way street, involving both losses and gains. When one named something, Luzin thought one gained in effectiveness, what he called, quote, new successes due to definition, unquote, but one at the same time also lost what he called, quote, the foggy and dark parts our intuition whispers to us. Thus, to Luzin, naming and definition are the awkward, incomplete, and inadequate tools that we must by necessity use in order to do mathematics, but which fall far short of encapsulating the entirety of the objects they allegedly describe. Luzin saw this as being at the heart of the field of mathematics he created, which is called descriptive set theory. According to French rationalists like Borel, Lebesgue, and Bayer, one should follow Descartes and, quote, commence with objects the simplest and easiest to know and ascend step by step to the knowledge of the more complex, unquote. But Luzin differed fundamentally with this form of logical reductionism. To him, the entirety of an object is far greater than its individual characteristics that might be named or described. Dmitry Yegorov and Nikolai Luzin are generally credited with creating the Moscow School of Mathematics, which by the mid-20th century transformed Moscow into one of the greatest, if not the greatest, single concentration of mathematicians in the world, and had an international.
Now, we might have thought that to build something as sophisticated as a universal computer, we'd have to build up all kinds of stuff. We'd in effect have to have this whole civilization that figures out all of these different kinds of things. But actually, what the principle of computational equivalence says, and what we found out is true, is that actually out there in the computational universe, it's really easy to find universal computation. It's not a rare and special thing, it's ubiquitous. And for example, it'd be easy to mine from the computational universe, say for the particular case of practical importance of making molecular computers or something. Well, okay, the principle of computational equivalence has other implications too that are pretty important. One of them is what I call computational irreducibility. See, a big idea of traditional exact science is that the systems we see in nature are computationally reducible. We look at those systems, say an idealized Earth orbiting an idealized sun, and we can, with sort of all our mathematical and calculational prowess, we can immediately predict what those systems are going to do. We don't have to trace every orbit, say. We can just plug a number into a formula and immediately get a result, using the fact that the system itself is computationally reducible. Well, it turns out that in the computational universe, one finds that lots of systems aren't computationally reducible. Instead, they're irreducible. There's no way to work out what they will do in any reduced way. There's no choice but just to trace each step and see what happens. It's actually pretty easy to see why this has to happen, given the principle of computational equivalence. We've always had kind of an idealization in science that systems we study are somehow computationally much simpler than us as observers that study them. But now the principle of computational equivalence says that that isn't true, because it says that a little system like Rule 30 can be just as computationally sophisticated as us with our brains and computers and so on. And that's why it's computationally irreducible, and by the way, also why its behavior seems to us so complex. Well, computational irreducibility has all sorts of implications for the limits of science and knowledge. At a practical level, it makes it clear how important simulation is and how important it is to have sort of the simplest possible models for things.
Whoa, math.
Whoa, math.
Whoa, math.
That says that simulating yourself is either slower, less detailed, chancier, or all of the above than actually being yourself. And the nice computer science version of this is called the Hartmanus-Stearns theorem, a beautiful, as Scott will tell you, beautiful theorem from computer science from 1961 or sometime like that, which says that to predict with certainty what you will decide to do an hour from now takes more than an hour. It takes more computational resources, because asking you the question, yourself, gee, what am I going to be doing in an hour, is like a lot slower than just doing it, okay? So, and this is true, okay? So sometimes any system that can actually contemplate, ask itself the question, what am I going to do in an hour, often won't be able to answer that. This is true whether the universe is deterministic or probabilistic, irregular, chaotic, classical, quantum mechanical. These are my like kind of Keith Haring-like pictures of a quantum thing with like little. Sorry. And so I'd like to propose, and by the way, this is I have a paper on this published in the Philosophical Transactions of the Royal Society, where all the theorems and everything are presented in gory detail. It's called A Turing Test for Free Will. You'll find it on the archive. There was a good Slashdot conversation about this a month ago. A Turing test for free will. So let's like ask these questions. This is a self-administered test, right? Because like unlike the real Turing test, you know, you should give it to yourself because if you cheat, you have only yourself to blame. Who are you hurting? Just you yourself, okay? Are you a decider? So are you making a decision? Can you model your behavior and maybe that of other things around you? And then the last one is, can I predict my own decisions? And that, of course, is a trick question because, because you won't be able to do this. If you answer the first two questions correctly, you cannot do the third. This is just a mathematical theorem about anything that is trying to predict itself. And let me give it as an example, George.
In fact, you see, I would say that how do we use computers in most things? If you want to solve some or simulate some problem about how stars behave or something, and you have a calculation you want to perform to see what it's going to do. Well, you supply the understanding, the computer does the calculation. It's a symbiotic relation we have with computers. That's fine. I have no problem with that. But it does seem to me, okay, the answer that the computer produces, it hasn't the remotest idea what it is, what it's for. You have to supply the understanding. So it seems to me the understanding is what the computer doesn't have. And now I've had three words here. I'm not going to define understanding. I don't know how to define understanding. The three other words I don't know how to define either. Intelligence is one of them, and awareness is another. All I'm saying is that they seem to depend, at least intelligence, whatever it is, I would think depends on understanding, because I wouldn't like to say of an entity that it is intelligent if it doesn't possess understanding. That certainly seems to me a natural use of words. Likewise, I would hesitate to say that an entity possesses understanding if it does not possess awareness. So it is related to this consciousness issue. Awareness is an aspect of consciousness, so it seems to me so is understanding. This doesn't say that computers couldn't have it. It's just saying that they're interrelated in this kind of way. So if understanding can be shown to be beyond computation, and that's the sort of argument I've just been trying to present you with, then intelligence is not a matter of computation. Moreover, certain aspects of awareness, and perhaps all, are beyond computation also. So that's my position here, is that these things are beyond computation. Now I want to get slightly more technical, and I hope you'll bear with me here.
And if you don't know, now you know.